And I'm delighted to have this opportunity to give a presentation here. A presentation that is not so wide in scope. For instance, I'm not going to mention any computational methods in this presentation because I decided to keep the focus rather narrow so that it's possible for me to convey ideas at a relaxed pace. It's about exterior shape calculus, and this is a blend of two fields. It's a blend of exterior calculus, calculus of differential forms, central toolkit in differential geometry, and of shape calculus, which is a rather thriving field while studying the change of functional solutions under variations of shape. And it's not hard to imagine that it has a close connection with shape optimization, and shape optimization is important in particular in engineering. In my presentation, which is based on joint work with my former postdoc Jingzhi Li, who is now a professor in Shenzhen, well, we have tried to bring these two fields that so far were rather disconnected together. And in my presentation, I would like to convince you that this is a worthwhile effort, that shape calculus can really benefit from the toolkit provided by differential geometry in the form of exterior calculus. So, now, shape calculus is concerned with studying the shape variation of things, of functions of shapes. So the common setting is the following. Imagine you've got a big ball. It's called a hold-all domain. Everything's going on in there. And then inside you have a set of shapes. Since in the back of my mind I always think of boundary value problems, I call it a set of domains. Well, there are many ways to define these. Let's say we consider all smooth domains contained in this hold-all domain. And then if a function defined on this set of shapes that so far has a precious little structure. And there are two kinds of functions that I call shape functionals and shape dependent functions. A shape functionals is the simplest representative, it's just real valued. This is what is tackled by shape optimization, for instance. More complicated is a shape dependent function. So you map from the shape set into a function space, and to make matters worse, this function space may also depend on the shape, so it's a fairly complicated concept. There are simple examples for shape-dependent functions, and main examples are provided by boundary value problems defined on omega. Here, simple Dirichlet boundary value problem, and of course, U depends on omega. So this is an example of a shape-dependent function. Of course, you will appreciate that in order to regard U as a function of omega, the data have to be a bit more general than usually required for boundary value problems. We have to be able to make sense of f and g, on the whole hold-all domain. So a shape-dependent function, and shape-dependent functionals are often derived from shape-dependent functions. So when you have PD-constrained shape optimization, then you encounter shape functionals like this that depend on the solution of a boundary value problem on omega, and so they themselves become functions on the shape set. So this is the context of shape-dependent functions. And now shape calculus studies the behavior of such functions under variation of shape. Properly speaking, it's differentiation with respect to shape. But now let me first introduce the second ingredient, because not everybody may be familiar with exterior calculus. I'm going to do this in a very intuitive way, from the so-called integral perspective, which, when you want to make it rigorous, is more complicated than the pointwise perspective, but it gives much more intuition, in my opinion. So, exterior calculus deals with differential forms, and differential forms can be assigned a so-called order. So we talk about L forms. And now, when I mention an L form, what I have in mind is something that can be integrated over an L-dimensional surface with orientation. For instance, a zero form, well, can be integrated over something zero-dimensional. This is point evaluation. Zero form is nothing but a standard function. A one form is defined by curve integrals. It can be integrated along curves with an implied direction. This is a one form. Two forms is integrated over oriented surfaces, and a three form is evaluated on volumes. And this is the intuitive, say, notion of a form. It's a mapping from oriented L-dimensional surfaces to the real numbers, with some continuity properties, of course, but that are rather difficult to characterize. And it has to be additive, so when you have two disjoint surfaces, and then the values just add up. So this is the idea of an L form that you should have in mind. Something that can be integrated over an oriented L-dimensional surface. And intuitive understanding has quite some benefit when it comes to understanding the calculus of differential forms. So, there are two reasons why exterior calculus and shape calculus have natural links, in my opinion. The first reason is that, second order boundary value problems play a central role in shape calculus in the context of PD constraint optimization and so on. And second order boundary value problems nicely fit the framework of exterior calculus. For instance, this one, there's reaction diffusion. Yes, reaction diffusion problem, a scalar boundary value problem, but also the boundary value problems from electromagnetics. They all turn out to be members of the same family when you view them from the perspective of exterior calculus. Because exterior calculus permits us to recast them in a single formula in the form of a general second order boundary value problem. And this is the formula with a lot of symbols that are fairly standard in differential geometry, but you may not be so familiar with them. So here we have the so-called exterior derivative, the differential operator, the D. Then we have so-called Hodge operators that introduce something that could be labeled a coefficient into the model. And we've got trace operators that make it possible for us to define boundary conditions. And now, the unknown here is an L form. And the order L is still a parameter. And when you choose different values for this parameter, then you recover the boundary value problems listed above. L equals 0. Zero form, I told you, are just functions. And we get this scalar second order elliptic boundary value problem, and for L equal 1, the typical boundary value problems from electromagnetics. Now, what is the connection? The connection between the general formulation and this concrete vector analytic way to write the boundary value problem is established by so-called vector proxies. In fact, vector proxies are based on a special choice of bases. They're based on choosing coordinates. And here I've chosen just regular Cartesian coordinates. Because when we choose Cartesian coordinates, for instance, in 3D, then it's possible to establish an isomorphism between differential forms and functions and vector fields. So here it's listed. 0 forms are just plain functions, but 1 forms can be identified with vector fields. So can 2 forms, and 3 forms in 3D again can be represented by functions. And now, once you fix this isomorphism, this particular one based on the Cartesian coordinate system, then you can, of course, express the exterior derivative and the other operators in the exterior calculus through operators on vector fields and functions. And this is what I've done in this table. So the Hodge operator just becomes multiplication either with a coefficient function or a coefficient tensor. The derivative d becomes one of the classical vector analytic differential operators. And the trace, well, for 0 forms it's the point trace, for 1 forms tangential trace, for 2 forms the normal trace, and 3 forms don't have a meaningful trace. So this is the translation table. And whenever you have a formula expressed in differential forms and you consider it, say, in 3D Euclidean space, you can employ this translation table to rewrite everything in terms of classical vector calculus. So formulas in exterior calculus, if they make you feel uneasy, then translate back in the concrete 3D setting. But of course, exterior calculus is more general. It's, well, covers any dimension. It will be extended to manifold, and in particular, you don't have to fix a coordinate system in advance. But now let's do the translation, and then when you choose L equal 0, then the d acting on u becomes the gradient. The Hodge is just a multiplication with this coefficient tensor. And then the Hodge changes the order of the form so that the second d now turns out to be a divergence. And the same for L equal 1. We get, of course, a completely different differential operators in vector calculus, because now the orders of the forms are different. So this is the first connection. And this is why it's very useful to think in terms of second order elliptic boundary value problems from the perspective of exterior calculus, because then you can treat them all at once. You've seen all these boundary value problems are members of a single family. And so from now on, I won't write down usually concrete boundary value problems in vector analytic notation, but I will regard them, I will rather consider the general second order boundary value problem expressed in exterior calculus. So this one. And this gives us a shape-dependent differential form as a solution. For instance, this one, call it the Dirichlet boundary value problem, and concrete incarnations we have seen. And of course, these boundary value problems, when you look at them, well, from a rigorous perspective, the most convenient understanding is in a weak form. Weak form, no problem in exterior calculus, because we also have a multiplication of differential form. This is this wedge product. And so this is the weak form of the general second order boundary value problem that I would like to use. You see, when you have functions, so zero forms, then it's just alpha gradient times u multiplied with gradient of a test function. Eta here is the test function, the test form.
May I ask a stupid question? What do you mean by d/omega? In the first line.
D is step.
Yes, step minus.
This is where?
Yeah,
first
how is it
line.
an independent L space?
Ah.
But
Yes, whether it's defined on omega or on the whole domain. So
why is it important to have the weak form?
it will be.
I mean, I know that everybody else here would be fine with the weak form, but let's ask this question.
Why is it important? Because this is a fairly straightforward concept of solution. When you use the strong form, you have to worry a lot about regularity. The weak form is also the form that is then the basis for finite element discretization that I'm not going to address today, but which is usually employed then in the numerical approaches to shape calculus.
But you want to see this thing changing the omega, right? That's the,
Yes, and you will see that the weak form,
changing the omega.
the weak form is also very convenient for, well, finding out what this shape derivative is that I'm going to introduce in a minute. Be patient. This will be a core point in my presentation. All right, so this is actually now the starting point, the weak form. The weak form is posed on a Sobolev space of forms, but this is nothing new because for the different orders of the form, this is just one of the standard Sobolev spaces, H1, H curl, H diff, that most of you know. Now, we want to study the change of this shape-dependent differential form under the variation of shape. We want to differentiate it with respect to shape variation. And this is, of course, at this point, a fairly murky question. How could you approach it? What do we do in, say, classical calculus in order to introduce differentiation? We first look at directional derivatives. So we look at the derivative along a curve in shape space. And then in the second step, once we have directional derivative, we can study whether they can be glued together into something, well, you could call a Fréchet derivative. And this is also the approach adopted in shape calculus. First, we study curves in shape space. And there's one way to define curves in shape space. There are several. This is my favorite, so-called velocity method. You cover the whole all domain with a velocity field, sufficiently smooth. This velocity field induces a flow. So induces a one parameter family of diffeomorphisms of this whole all domain. So it's a family of flow maps. And now the flow carries along domains inside the whole all domain. Let's assume the inside The blue curve is the domain omega, and then we have a flow field, and then omega is deformed under the flow. And so a vector field induces a flow which naturally gives a curve in shape space by transporting domains. And then we can differentiate along this curve and get a directional derivative. And so shape calculus first talks about directional derivative in the direction of a vector field, when you agree with the velocity method. And now this is now the second main argument why exterior calculus is highly relevant for shape calculus. Because now you see in the velocity method, the concept of transport is crucial. You transport domains. For differential forms, transport is the most natural operation. Oh. Remember my intuitive understanding, and now, of course, when we have a flow field, this flow also transports these curves and surfaces over which the forms are integrated, and this naturally defines a transport of a form. And this is called the pullback. This is the formal definition. What do? We transport the, say, the test surface. And then we track the value of the form, and this defines the pullback over the original surface. So this is the definition of this transport of a differential form. So you move the test surface, and then you define the value of the transported form on the original surface as the value of the original form on the moved test surface. This is how you can define this pullback. So there's a natural concept of transport of a form. And then we can wonder, how does, well, the value of the form change as you move the test surface? This is this derivative. So you move the test surface with the flow, and you watch the change of this integral.
And the direction B?
Excuse me?
The direction B, how do you choose? The direction.
V.
Any. Just a vector field defined on the whole domain. Because now we look at directional derivatives. So V so far is just a fixed vector field defining a curve in shape space, and now we look at what happens along such curves. So V is fixed, and once we have V, we have the family of diffeomorphisms. So we can transport our test surfaces, define the transport of a differential forms, and then we can also define the material derivative, which is a device measuring the change of the form as we move along with this velocity field.
So, can you repeat what is the test surface? What do you mean by sigma?
This sigma is, say, for a one form, it's just a curve. You have a
So
curve.
it's where you're applying your omega. So
Yes.
should it be something like the boundary of the domain? But should we understand that as the boundary of the domain?
It can be any
Or the
curve
domain
in the
itself.
whole domain. This, because, as you see, I consider this for any admissible test surface, for all test surfaces. This is why this is really a definition here. Because once I have fixed the value of a form for all test surfaces, I have defined the form completely.
ML is an oriented dimensional submanifold. Is that smooth? Smooth manifold?
This is a tricky question. This is when you want to answer this rigorously, then you have to dig into what is called geometric integration theory. For my purposes, it's just, well, say piecewise smooth curves, piecewise smooth surfaces. This is a very deep theory, and off the top of my head, I could not answer your question right now because it's a very difficult question. What kind of manifolds are admitted? Because to this integral perspective of forms is the so-called perspective of currents, which is well, fairly intricate.
I mean, presumably integration has to be defined, and that's what you need.
Yes.
This, in a sense, would be the point of view, not only on numerical language, but some applied, is smooth enough that you can allow you to integrate.
And you can
No.
also add them and do stuff.
The really difficult aspect here is when you have a form, what is meant by this vague notion of continuous dependence on the test manifold. This is really difficult to make rigorous. So
that's why sometimes people, they assume they have a lot of regularity.
well, probably here you can even assume that you have only smooth curves, because then you can just approximate any non-smooth curve by smooth curves. All right. So this is the material derivative, and here what I've used is just the definition of the pullback. So the material derivative can be rewritten now, since this integral is here over the same test surface, and say since all test surfaces are admitted, then both integrands have to agree, and this gives the definition of the material derivative. The material derivative is a Lagrangian concept. So what is it when you think about a function? So you follow the flow and then watch the function value change. This is the material derivative. Basic concept in all of continuum mechanics. Then you can pull apart the material derivative. And this is what I'm going to do now. You can do it in various ways. Maybe we should call it a product rule, because now look, this is the definition of the material derivative. And now this transformation depends on the pseudo-time. Time defining the flow, the parameterization of the family of these homomorphisms. But so does the form. So you have a pullback depending on tau, form depending on tau, and this is a more or less a bilinear operation in a sense. And now you can apply a sort of product rule and pull apart the differentiation of the two ingredients. So the first one is just the differentiation of the form with respect to pseudo-time, because the pullback for tau equals 0 is just identity. And the second is, well, the form is not differentiated, but if we differentiate the pullback. And this is now a new and very important operator in exterior calculus, because this differentiation of the pullback gives us the so-called Lie derivative. So what we have written the material derivative as a derivative of the form and derivative of the transport, which is the Lie derivative. And the Lie derivative is a very convenient operation because it can be rewritten in terms of more elementary operations. And this is the so-called Cartan's magic formula. This is one of the fundamental relationships in the exterior calculus. You can rewrite the Lie derivative in terms of the differential operator D, and another operation called the contraction. And the contraction is something simple. And to make you believe me, I give you the contraction for our vector proxies. This is the last line in this translation table. I shouldn't block your view. So, and you see contraction with a vector field is a very simple operation. Just the inner product for one forms. For two forms, it's the cross product. And for three forms, just the multiplication of the function representative with a vector field. Contraction reduces the order of the form by one. And this formula for the Lie derivative then paves the way for very powerful and rather simple formulas in shape calculus. We'll see this in a moment.
Can you explain the first term on the previous slide? I'm really not. I understand the Lie derivative very well. Yeah, the slide before this one. Sorry. What's the partial s of omega 0? I mean, I'm not getting that. What's
Oh,
the Lie derivative? I understand. I don't understand why you get something different.
No,
from
well,
that. Yeah.
the differential form omega is shape dependent. Now we follow this curve in shape space. And since omega, little omega depends on capital omega, then it becomes S dependent. And this is meant by this.
So, I mean, but your shape dependence just comes from integration of the domain, or is there another shape dependence that you've got?
So far, this is a generic shape dependence here.
Oh, okay.
I assume that this little omega depends on capital omega.
Oh, okay.
And when we
okay, that's fine.
regard it along a curve, then it becomes S dependent.
Yeah,
This is then this derivative with respect to S.
that's fine. Okay, thanks.
Sorry, this is sometimes a bit complicated because many things are coming together.
Yeah, that's fine.
So there's. I hope I'm not rushing through these things too quickly. Okay, so we have. Lie derivative in vector proxies. Just to show you that the formulas of exterior calculus are really simple compared to what you face when you work out everything in classical vector analysis. So we can use Cartan's formula with the translation table to translate back. These are the formulas for the pullback in vector calculus. Reasonably complicated. And then you can really work out all these identities with classical calculus, but this is very tedious. But here we get them right away from Cartan's formula with the translation table. Now this is the Lie derivative, and now you have just the different ingredients. This is one differential operator, this is the contraction, and this is the other. So this makes it very easy to recover the formulas in Euclidean space. Now, shape derivative. So far now we have seen this material derivative in exterior calculus of a shape-dependent form, the directional derivative in the direction of a vector field. And now let's step back and return to the original problem. We have a shape-dependent form. And now we want to track its variation under the variation of shape. And the first candidate for doing this would be something that we have already seen, is the material derivative. Does the material derivative work? This is the definition of the material derivative. But unfortunately, it does not work. Why? Consider this setting. So we have a circular domain, and the vector field induces a rotation. So under this vector field, the domain does not change. So the shape derivative of the form in the direction of this vector field should be 0. Now when you consider the case of a 0 form, simple functions. If the function is non-constant on omega, then you would record a non-zero material derivative under rotation.
Well, it might be an invariant function. It might be a function of the radius.
Yes, of course. Sorry, I wasn't precise enough. Yes, if it's a function that is not a function of the radius, yes, otherwise it shouldn't be a killing vector field. Yeah. Yes, if it's a function that is not a function of the radius, then you have a non-zero material derivative. So the material derivative is not the right device to express a shape derivative. Because the shape derivative actually should be an Eulerian concept. Because when you define the shape derivative like this, so you have the form, and now I assume we have point evaluation. For the 0 form, this is clear. Then you fix a point and then stay there and watch the change of the form. This is an Eulerian concept. And this is, of course, when we have this rotation of the domain, this is what will give 0. Because the domain doesn't change, so omega doesn't change, so the point value doesn't change. So this Eulerian derivative seems to be the right concept. But the Eulerian derivative is not so easy to work with. But fortunately, it can be connected to the material derivative. We'll see this. But the Eulerian derivative, this local shape derivative, is the right concept. And this is then defined as the shape derivative. One remark, here I've written this d prime. This means this is in the sense of distributions. Why? Well, when you change the domain, then of course values close to the boundary may fall out of the domain, or some values may enter the domain. And this is a problem. When you view the shape derivative from perspective of a distribution, then you have test functions that are compactly supported inside. So the support always has a positive distance from the boundary, and so when you keep the variation small enough, you don't have to worry about behavior at the boundary. So this is why this local Eulerian shape derivative is rigorously defined to begin with only in the sense of distributions.
I'm confused. I'm sorry. Can I ask
Yes.
you? So you had the material derivative with respect to S.
Yes. Mm-hmm.
But now you have changed it and you have it with respect to omega. How should I understand this? And what does it mean the second line as well? What do you differentiate with respect to omega? What does it mean?
This is a notation, nothing else.
All right.
This
Okay.
this is the definition of this symbol. This is the same as on the previous slide. When you fix the vector field, then you get a curve. Then this is the capital D over capital S, over ds, sorry. So here I just allow general vector fields. So I introduce this velocity vector field as a direction parameter in the sense of, a Carteau derivative.
You
So this
differentiate
is-
in that direction?
I differentiate in the direction of V. This is the material derivative in the direction of V. And this is the shape derivative in the direction of V. So
Which means that you're just differentiating the form.
yes, the shape derivative is something local. I keep the point fixed and track the change of the value of the form. Sloppily speaking. More rigorously, you have to do this then in the sense of distributions. So multiplying the test function, test form, and then everything can make sense because point values may not be well defined.
How's this related to the derivative then?
Next slide.
Next one.
So, connecting material and shape derivative. Because the material derivative is a simpler concept. This point evaluation is hard to deal with. But now, let's make the connection. So, we cannot use the material derivative to measure this shape dependence. But there's a way, yes, this is this product rule, the pulling apart of the material derivative that rewrites it as a purely local derivative and the Lie derivative. And so, well, this is just the shape derivative.
Okay, so that's what you showed us before, right?
Yes, and now it's reinterpreted in the context of shape calculus. Because now we have seen that the shape derivative, this elusive guy, this tracking of point values, can be expressed by material derivative minus Lie derivative. This is now the formula from differential geometry now put into shape calculus context. And the benefit is that these two things are well understood. Questions at this point? But now let's compute this shape derivative, this thing, for solutions of these second order boundary value problems. Neumann problem first. By Neumann problem I mean this boundary value problem written in its general form. And now I make a point that the easiest approach is really based on the weak formulation. Because you can rewrite this now in weak formulation in such way. We multiply with a test form, we do this integration by parts, which is available for differential forms, this is Stokes' theorem. And this is what pops out, and this is, well, the standard variation formulation of a Neumann problem. It's posed on the entire Sobolev space, and here I consider the Sobolev space on the whole all domain. But this doesn't matter because we are only interested, of course, in what's going on inside omega. But of course, it's much more convenient when you can choose a function space that does not depend on omega. You can do this because outside omega, well, it's of no interest. And now I want to compute the shape derivative of this omega. What I do is I do shape differentiation on both sides in the sense of a Gateau derivative to begin with. Of course, I fix a vector field and then compute this directional shape derivative on both sides. So let's do it. But of course, in order to do this, we have to understand how to differentiate integral expressions with respect to omega when the integrals are either on the left over omega or are defined on the boundary of omega. So let's look at this particular task. So we have such an integral expression. I'm giving you the formula for, say, an L form defined on an L-dimensional or integrated over an L-dimensional surface. The form depends on omega, and of course, also the surface is carried along by the flow. So, this is the, well, what you would call the derivative with respect to the flow parameter. This is the formula that we had for the material derivative, because this is nothing but the integral of the material derivative. Cartan's formula. And then I can here use Stokes' formula. So the d, when integrated, gives an integral over the boundary. And this is the general formula for the, say, directional shape derivative of an integral. And now we can look at the special cases. This is the volume integral form. This is what we have on the left of the variational equation. Let's do this. For volume integrals, this is this omega is a D form. And now when you differentiate a D form, then it evaluates to 0. So this part can be dropped, and this remains and gives a boundary contribution. And now I would like to point out a difficulty in shape calculus, because now you see that you have to integrate well, the restriction of the form over the boundary of omega. And of course, for this to be well defined, you need much more smoothness than required for the original integral. Well, think of a volume integral. The function, well, it's enough if it's in L1. But of course, an L1 function doesn't have any meaningful trace. So for functions that allow the volume integral to be defined, this expression is not necessarily defined. So shape differentiation invariably entails, well, stricter smoothness requirements. And this can be observed throughout. So for vector proxies, well, vector proxy of a D form is just a function, we get this one. And here you see, if u is an L1 function, then the integral is defined, but of course this need not be defined. On the right of the variation formulation, we had this surface integral. Now let's look at this case. Now we are of a D minus 1 dimensional surface. This is the boundary of the domain. And we integrate the D minus 1 form. And we use the formula again. And now this term drops out because the boundary of a boundary is 0, the empty set. So it's only this term that remains. And this gives us this contribution. Again, we need more smoothness. Because now we have a derivative that we have to integrate over the boundary. So same observation as before. For vector proxies, for the D minus 1 form, the vector proxy is a vector field. And its shape, the shape derivative of this boundary integral involves, well, also this extra boundary term. And you see there's a divergence, so you need a sufficiently smooth divergence here. Now, we have the tools to tackle this variational problem. So, first, on the left. On the left, we have an integral over omega, and the entire integrand is a D form. So, it now plays the role of this mu. And so we just rewrite these terms for this more complicated expression. And what we get is highlighted here. This is the, oh, sorry, pressing too long. Where do, here, yeah, this one. The shape derivative of the whole thing is just the expression with omega replaced with the shape derivative. Why? Well, the test function does not depend on shape. This was, by the way, one reason why I mentioned that the spaces do not depend on omega here, because you can then choose the test function independent of the shape. When you differentiate this with respect to shape, then all that remains is shape derivatives of omega. And since everything is linear, you can just pull them in. And then on the left, from this term, we just recover the usual bilinear form for the shape derivative. On the right, here, we have boundary integrals. And this is the fault of this term. Because now plug in from u this one, and then what you end up with is this. And then from the boundary term, entering through the Neumann data, we get another term on the right hand side. This is another contribution. Now let me talk about the structure of this problem. Because what we have arrived at is a variational problem for the shape derivative. Because eta is a general test function. So this has to be satisfied for all eta. We imposed no restrictions on eta. Eta is from the full Sobolev space. And now you see, this is a variational problem with the same bilinear form. So it's of the same type, but with different right-hand side. And the right-hand side here is, well, an expression that is very similar to this right-hand side. It's also wedge eta, so, and an integral over the boundary. So it's in a sense a Neumann problem again, but the Neumann data are now given through an expression involving the solution omega and also the vector field v. And this is the general structure. So whenever you compute the shape derivative and you do it for a linear variational problem, what you end up with is a variational problem of the same type with a modified right-hand side. And what we also see here is the smoothness requirements. Because what we have here now are derivatives. Imagine the case L equals 0. So standard functions, Sobolev space H1. Then this would be a gradient. But this gradient has to have a trace on the boundary. So you can no longer admit the full Sobolev space here. You have to assume that the solution omega is smoother. Otherwise, these expressions, these variational problems for the shape derivative will not be well defined. So it's again a Neumann problem, but with Neumann data, depending on the solution of the original Neumann problem and the vector field, but the original solution has to have a lot of extra smoothness so that this is well defined. So shape calculus, well, is confined to a boundary value problem that have solutions with a lot of extra smoothness. If this extra smoothness is not there, then there is no, well, shape derivative that you can characterize as a solution of such a variational problem. Then you can do something else. Then people have resorted to so-called ultra-weak formulations to give a meaning to the shape derivative, but I'm not going to address this here. So we can rewrite this term on the right-hand side to extract really a Neumann boundary condition, because what you can do is you can shift a derivative onto the other side using integration by parts on the boundary, and then this is what you recover as the Neumann boundary condition for the shape derivative. Fairly complicated term, but you see it involves a lot of differentiation on the boundary of the trace. And this is of course only possible when everything is sufficiently smooth. This was also the reason why I've in the beginning restricted everything to C1 domain and smooth vector fields. Then you won't encounter any difficulties. The vector field is merely Lipschitz, then a lot of extra issues crop up. Now, just to give you an idea that these formulas are really useful. For instance, now we can easily, by using the translation table, write down the shape derivative of solutions of eddy current problems. Remember, this is the case L equal 1, the electromagnetic boundary value problems. This was the boundary value problem. And now the shape derivative, this is the general formula, and then you can translate back. And the shape derivative of a solution of such an eddy current problem is another solution of an eddy current problem where you have, say, magnetic boundary conditions of this kind. Well, looks well complicated, but with one formula in exterior calculus you can recover all of them. Brief remark only about Dirichlet boundary value problems. With Dirichlet boundary value problems, we get stuck if we use the standard variational formulation. Because in the standard variational formulation, the test space depends on the domain, H10 or H curl 0, whatever, depends on the domain. And this is a no-go. Then you can't do all these differentiations anymore. So what can one do? One way is, say, you switch to the mixed formulation, because then the boundary conditions are no longer essential in the variational formulation. So you don't have to impose them on the test space, and then you can continue. So for instance, you can use this. This is now for zero form standard mixed formulation. You can differentiate it, both sides, also the boundary terms using the formulas, and then you get the variational problem for the shape derivative. This is written here, all the different terms. And these are the extra boundary terms that define boundary conditions for the shape derivative. And again, you need substantial extra smoothness so that this is well defined. Now, I'm running out of time. So, I'd like to discuss the transmission problem. Well, only briefly. So, I'm going to skip the technical part. Because transmission problem is very interesting and it bothered us a lot. Very simple transmission problem. You have essentially a Dirichlet boundary value problem with jumping coefficients. And they are piecewise constant, and the jump is defined by this domain omega. They have one value inside omega and another value outside. I say, well, this is really straightforward. You use a variational formulation and you just plug in the discontinuous coefficients. So what the heck is the problem? There is a problem. And this is an interesting aspect. So, because the shape derivative, it erodes the regularity. Let's see why. This is the formula connecting Lie derivative and material derivative and shape derivative. The material derivative is perfectly harmless. When you have a smooth vector field, then the material derivative will not affect the regularity of the function, because it's just transport, and under a smooth vector field transport, the transported function stays in the same space, same Sobolev space, so the material derivative, since you take the limit, remains in the space. No problem. So this is harmless. This remains in the Sobolev space. But the Lie derivative, when you look at it from the point of view of the vector proxies, you immediately see there's a differentiation. The Lie derivative reduces smoothness. And so this reduction of smoothness through the Lie derivative, of course, affects the shape derivative, because the Lie derivative involves a first order differential operator, so the shape derivative can only be in a reduced smoothness space, and it will be an L2 space if you start from this, the Sobolev space. So shape derivatives can have reduced smoothness. And there's a nice 1D example that I've contrived with my co-author. So 1D transmission problem, just an interval Dirichlet problem, and you've got a discontinuous coefficient. And then you can compute everything. You can compute the solution depending on the position S of this jump. And then you can compute the shape derivative. You just differentiate pointwise with respect to S. And you observe this. The solution just has a kink, it's still continuous, so H1, nice. The shape derivative has a jump, merely L2. And now you see the complication for a transmission problem. When you use the standard variational formulation, you say, I have a discontinuous coefficient, but I don't care. I pose the variational problem on H1 on the hold-all domain. You can never get the solution for the material derivative, because this should be discontinuous or can be discontinuous. So it cannot be captured by the H1 space. So you have to choose a formulation, a variational formulation that can cope with discontinuities across the boundary of omega. So you use a variational formulation, say, so-called of multi-field type, where you impose the continuity of the function only weakly, so that it's not built into the space, but it's only enforced in the variational formulation. Something like this. So you separate the two parts, and then you have this Lagrange multiplier type term that enforces the continuity. And with this you can do shape calculus, because then you have this possibility of a jump in this space. We got separate Sobolev spaces inside and outside. And this is what has to be done here to get a meaningful variational problem for the shape derivative. I'm going to skip all the technical details here. Of course, now you can differentiate, and but let me jump right to the conclusion. So you've seen this marriage of shape calculus and exterior calculus. It gives you rather powerful formulas and unifying formulas. In particular, we have this formula, which is very convenient, that, well, parallel to the usual formula for the material derivative, we can also express the shape derivative through material derivative and Lie derivative. And then use the nice formulas for the Lie derivative. And we have seen that, of course, what another message sent by this formula is this loss of smoothness. Because the Lie derivative differentiates, so it reduces the smoothness of its argument. Then, Lie derivative formulas are very convenient, and you can get very general formulas for the shape derivatives, for Dirichlet problem, Neumann problem, transmission problem, for all orders of forms in any dimension. So you can, in one sweep, treat all these cases. And this is interesting because then on a few pages you can recover all the results that for all the individual cases have been obtained by these tedious vector analytic computations over the years. So then you use the translation table and you get all the formulas from these papers. So this is an indication that it's worthwhile using the general calculus because it saves you a lot of work. And it also is a safeguard against a lot of errors because the formulas on the level of exterior calculus are more compact and, well, it's clearer what you should get because you've got an exterior derivative, you have a Lie derivative, and so it's more straightforward. Nevertheless, you have seen it's still a lot of technicalities involved. You have to be, careful with the integration by parts on the boundary with smoothness assumptions. The details you can read in these papers. I hope I have given you some general ideas and I've succeeded in convincing you that this blending of shape calculus and exterior calculus has been a reasonable idea. Thank you for your attention.